breath.
Good afternoon, everyone. My name is Chow from the Department of Photonics, National Yangming Jiao University in Taiwan. I would like to thank the organizing committee for inviting me to give a keynote speech at the VTC workshop on optical wireless communication for 6G. I have to apologize that I cannot join the VTC in person. It's my great honor to share some of my understandings in optical wireless communication for the 6G and space communication. This is our outline of my talk. First of all, I will talk about the motivation, followed by the fundamental of OWC system, the positioning, beam steering, and also the long range applications. Finally, I will give closing remarks. I would like to acknowledge some of my funding agencies, including the National Science and Technology Council and the ITRI in Taiwan. And also, I would like to thank my collaborators in Foxconn, Luminous, Georgia Tech, the Chinese University of Hong Kong, and the Fengzhou University. I would also like to thank my students and also my graduate students. Over the past few decades, the available RF spectrum has become very limited because of the exponential increase in the wireless traffic. OWC can provide new capacity and available spectrum. The combined visible light and also the IR spectrum is more than 2,000 times larger than the radio spectrum. Considering the right deployment of LEDs in the indoor environments such as offices, hospital, conference rooms, high density OWC auto cell supported by these LEDs can be achieved. These auto cell can provide high area capacity with negligible electromagnetic interference. As light doesn't penetrate walls, it can also provide additional physical layer security to enhance privacy. Recently, many people are talking about 6G. 6G network is expected to provide better performance than 5G. For example, the NTT Docomo put down some expectations for the 6G. It requires extreme coverage by integrating the space, the air, the terrestrial, and even underwater networks. It's also expected to provide massive device connectivity with high positioning. And this figure shows the European vision for the 6G network. It should have a higher capacity, higher data rate, higher device density, as well as higher location accuracy. As the OWC has a wide and unregulated optical spectrum, OWC can achieve several important KPIs for the 6G, while it may be very difficult to be achieved by using the present RF systems. OWC can allow laser beam to be directed to the space, to the air, and even to water for communication, producing a multi-dimensional network needed for the 6G. Now we talk about the fundamentals of the OWC systems. This figure shows a typical OWC system, including the transmitter module, the channel, and the receiver. For the channel, it can be mathematically expressed in these equations shown here, with the channel response factors, including the beam divergence, atmospheric attenuation, Poynting error, and atmospheric turbulence. For the first one, beam divergence. As light propagates, it tends to diverge. Hence, only a clipped portion of the optical signal can be achieved. This channel response factors is proportional to the aperture diameter of the receiver. This means increasing the receiver aperture or using multiple receiver can reduce this effect. The second one is the atmospheric attenuation. The laser beam is absorbed and scattered by the particles in the transmission medium. Depending on the weather conditions, the attenuation coefficient can vary significantly from 0.2 dB per kilometer in clear air to more than 200 dB per kilometer under heavy fog environment. The third factor is the Ponting error, which is due to the optical misalignment by wind, building vibration, foam expansion, etc. Common mitigation approaches include active alignment, increasing the beam width at the transmitter, or increasing the FOV at the receiver. The fourth factor is the atmospheric turbulence. The laser beam is aberrated, producing wavefront distortions and intensity fluctuations. This will produce turbulence-induced fading. Using multiple receivers or adaptive optic could reduce this effect. The advantage of OWC system is that it can provide much higher transmission data rate than the traditional RF systems. For this reason, researchers usually focus on increasing the transmission data rate. Due to the limited time today, I'll just briefly highlight some examples of the VLC work. There are also many other groups achieving very high performance VLC systems. This slide shows some example of the white light VLC transmission using blue laser diode with phosphor. We can see that OFDM with bit and power low are commonly used to enhance the spectral efficiency. For example, in this work reported in 2018, Wu et al. Studied the effect of phosphor co-doped with fluorescence glass. By thinning the glass from 1 millimeter to 0.7 millimeter, a high data rate of 4.5 gigabit can be achieved. For example, in 2020, we packaged a blue laser diode chip with phosphor and lens. Data rate higher than 6.9 gigabit per second with a transmission distance of 1.5 meter can be achieved. This work was highlighted in the electronic letter, and you can refer to this reference. To further increase the VLC data rate, WDM can be used. This slide shows some example of WDM VLC transmissions. For example, in 2015, Wu reported using RGB LEDs with the phosphor to provide an eye-safe transmissions. In 2019, Chong et al. Reported using RGBV LEDs. These are 4-color multiplex VLC system with the MEMS mirror for the beam steering. The system operates at 35 gigabit per second, covering the area of 39 square meter at a transmission distance of 4 meter. Besides WDM, bit and power low OFDM together with precision multiplexing can be used. Here, we achieved more than 40 gigabit per second reported earlier in here. Recently, micro LEDs show many advantages over traditional LED in the display industry. In addition, it can be integrated with displays, wearable devices, and solid-state lighting systems, enabling them to provide the display, lighting, and communication at the same time. Due to their small size, you can see here, micro LEDs have a very high current density and a shorter RC time constant, having a higher modulation bandwidth. Then nitride-based LEDs grown on traditional C-plane substrate suffer from efficient slope caused by the quantum confined star effect, QCSE. By growing the quantum wells on the semipolar plane, the polarization-related electric fields can be reduced. This can also result in a faster recombination and a higher bandwidth. In here, we achieved a green micro LED, which is grounded on a semipolar substrate and having a bandwidth quicker than 1 gigahertz. And we also apply bit loading OFDM data, and the transmission is quicker than 3 gigabit per second. By using similar approach, high bandwidth semipolar blue micro LED can be fabricated. And by adding the yellow phosphorus, we can produce white lights, as shown here. So here is the measured bandwidth. We can see that for the blue micro LED, it has the bandwidth quicker than 1 gigabit per second. With the blue together with the yellow phosphorus, the bandwidth about 800 megahertz can also be attributed. Recently, many efforts have been dedicated to develop indium gallium nitride red micro LED. Since red light emission requires a high indium content in the quantum wells, uh, the large lattice mismatch causes a significant number of defects in the quantum well. Here, superlattice layers are grounded for strain reduction. We demonstrate a red micro LED with a bandwidth more than 270 megahertz. And this work on the blue and the red and also the yellow green micro LEDs receive the top downloads in the Object Express and for research respectively. As discussed before, one of the KPI in the 6G is we required a high precision positioning. We can see that visible light positioning, we know that VLP can achieve a high precision position when compared with other technologies, particularly for the indoor environment. So here is one example of the VLP system based on the received signal strength, RSS. As the received optical signal strength decreases when the distance between the LED transmitter and the receiver increases, the RSS can be used as an indicator to identify the distance between the transmitter and the receiver. The idea is like this: the whole area will be divided into different positioning unit cells. By studying the IDs inside the unit cell can be identified. Once the unit cell is identified, the client or the receiver inside this unit cell can be precisely located by using the RSS. Machine learning techniques can be used to increase the accuracy. Here is a proof of concept demonstration. We performed it in a practical room with a client. It's a AMR. The unit cell consists of 4 LEDs, and the distance between the LEDs to the receiver of the AMR is about 250 centimeter. Here we use the convolutional neural network to enhance the data positioning accuracy, and we can see that the position accuracy can be less than 6 centimeter inside the unit cell. As VLP has received more and more attention recently, however, the VLP simulation software is not available right now. Here we proposed to transform the Dialex, which is a free of charge software, for the VLP simulations. We can use Dialex to relieve the burden for the machine learning training data collection when designing the indoor positioning system. Here we in this environment for the model trained by experiment, we have the FH error about 10.5 centimeter. By using the model trained by Dialex, the FH error is 11.1 centimeter. They're quite close. The slight difference between them can be due to the difference of light emission profile by the actual LED luminaires. Since inside the Dialex simulation, all the LEDs have the same ideal light emission profile. Another work we perform is that usually we train one unit cell. If we can apply the trained data to other unit cell, it can highly reduce the training burdens. And in this work, we use the transfer learning and also the position unit cell model duplication approach to copy the training data to this unit cell, and the result is quite promising. As mentioned before, one critical issue in the OWC is the pointing error. An active alignment using optical beam steering is desirable. There are several approaches of beam steering. One of them is using mechanical mirrors. They usually have coarse resolution, wider FOV, However, they're usually bulky, and the steering speeds are limited. Moreover, optical beam steering can be achieved by using emitter arrays. It can offer fine resolution, moderate FOV. It can be very compact. However, the operation mechanism could be complicated. Another non-mechanical approach is based on the liquid crystal spatial light modulator SLM. It allows fine resolution, small but with small FOV. One interesting feature for the SLM is that it can allow the wavefront control, allowing multiple beams manipulation. This slide shows one example of the optical beam steerings based on the optical phase array we did earlier. The OPA chip has on-chip laser diodes, SOAs, and a star coupler, and 30 phase shippers, and an array of edge emitters as the OPA output. The chip is fabricated on indium phosphide platform by Smart Photonics. The phase shipper can control the optical phases in the brand can control the optical phase in each branch. In order to achieve optical beam forming and beam steering, the relationship among the edge emitter array pitch D and the phase difference between the adjacent emitter, the delta phi, should be carefully considered. In order to achieve a a large FOV, the pitch should be decreased. However, decreasing the pitch D will increase the crosstalk among the emitters. So there's a trade-off. In order to achieve the beam forming and beam steering, the phase in each phase shipper should be carefully controlled. Here we used a generic algorithm to optimize. And this work was published in the OFC 2020 and received the top score. Besides, recently our colleague Yao Jiang has demonstrated in the Clio this year a silicon photonic-based optical beam steerer based on FPA. Deep beam steerer consists of focal plane array FPA for coarse steering, two micro heaters for fine tuning, and a shallow edged slab grating for light emissions. The FEA consists of 13 input waveguides channel and an on-chip metal lens for the tuning. Light from different channels, light from different input channels is sent to different propagation directions, allow horizontal beam steerings, and the heater can perform the fine tune. The dispersion diffraction from the slab grating allows vertical, allow waving dependent vertical beam steering. Here show the result. This is the horizontal beam steering, and for the vertical, we change the wavelength and produce the vertical beam steering. Another interesting beam steering device is the SLM. It can not only provide beam steering, but also support multiple beam divisions. But also support beam division and allow multiple user transmissions. The operation mechanism is like this. First of all, we generated and computer generated hologram CGH pattern in grayscale. This SGH pattern will be uploaded to the SLM. It will change the applied voltage to different pixels of the SLM, which in turn will produce different tuning for the liquid crystal and different phase shift. Hence, an artificial generated grading pattern can be achieved for beam manipulation. Based on this SLM, recently we have demonstrated an SLM-based 4-user audio-visual system using Llama. Llama here is employed to provide flexible data rate for different users. This is the first time a 4-layer successive interference cancellation SIC iteration was experimentally demonstrated in an OWC system. And you can refer to this reference. As mentioned before, besides the pointing error, another critical issue in the OWC system is the atmospheric turbulence. Besides acting as the beam steerer, the SLM here can be used as an atmospheric turbulence emulator. The atmospheric turbulence model used is the modified Won-Kalman model, including the large scale and small scale cells with different coherent diameter, which is known as the 5 parameters R0. The larger the R0 means the smaller the turbulence. As our collimator have a diameter D of 14.5 millimeter, we select the R0 so that the D over R0 is equal to 1, 5, and 10, representing the weak, medium, and the strong turbulences. Here show the CGH patterns we uploaded to the SLM emulator. And here is measured beam profiles by using our camera. We can see that at weak turbulence, the beam is quite uniform. However, under strong turbulence, the intensity as well as the profile is destroyed. Okay, based on this emulator, we proposed turbulent mitigation scheme by using a multiple aperture silicon photon receivers consisting of 4 vertical gradient couplers. They are attached to 4 germanium silicon PDs. This experiment here is generated OFDM signal at a fixed data rate of about 40 gigabit per second, launched to the emulator, and then received by this PD. And this graph shows the result of one of our vertical gradient coupler, which has a peak coupling efficiency of minus 2.8 dB at a wavelength of 13.8 nanometer and a 3 dB bandwidth about 16 nanometer. The germanium silicon PD has an active length of 40 micron and has a stronger absorptions at the shorter wavelengths. Here shows the measured bit rate using different number of receiver apertures of the silicon photonic receivers, processed with the maximum ratio combining technique to combine the four signal after the 4 PDs under the weak, medium, and strong turbulences. At weak turbulence, we can see that only one aperture receiver is enough to fulfill the HDFEC requirement, while at the strong turbulence, 4 aperture receivers are needed to fulfill the HDFEC. We also measure the outage probability. We can see that by using at the weak turbulence, the 4 aperture receiver can achieve 0% outage at the weak turbulence. For the strong turbulence, if we only use 1 aperture receiver, the outage is 100%. As the OWC offer high bandwidth, high data rate, and high directional transmission, as we see earlier, it has emerged as a preferred solutions to connect satellites. However, implementing the space laser comm is not straightforward. It can be divided into 3 transmission scenarios: the space to the ground links, satellite links where the satellites share the same orbit, and the intersatellite links where the satellites are in different orbits. They all have their own challenges, but the most relatively straightforward one is the intersatellite links with co-orbiting satellites, because the light is propagating in vacuum, and the relative geometry among the satellites is quasi-static. The space-to-ground link is most challenging because the optical signal will be influenced by turbulence, as we discussed earlier, and also blocked by the cloud effect. Although they are challenging, the 3 transmission scenarios have been demonstrated to be technically viable by many groups. And the industry is now considering about the scalability, the cost, efficiency, and the performance consistency over scale. Now, this is my closing remarks. Optical wireless communication is an emerging area where the research and development are growing worldwide. OWC can offer several unique transmission advantages and can achieve several important KPIs for the 6G, while it may be very difficult to be achieved by using the present RF systems. We have discussed the fundamentals of the OWC systems, different transmitters, positioning, beam steering, thermal mitigation approaches. OWC is rapidly evolving in indoor, outdoor, and space environments with challenges and opportunities. And this is the end of my talk. Thank you so much for your attention, and I'm also happy to answer any comments and suggestions and questions. Thank you so much.